All right. Next, we have Juan, who's going to talk to us about advantage alignment algorithms. So please give him a warm welcome.
Hello. I'm a PhD student at the University of Montreal, and today I'll be presenting this work. This is a joint work with my co-author Milad, my collaborators at the University of Montreal, and my advisor Aaron Curville. So hopefully by the end of this talk, I can convince you that there is this fundamental issue with the way we're doing reinforcement learning, and that we have to start thinking about the way multi-agent systems are going to behave out in the world. We've been thinking about this question for a while with our group, and what I'm presenting today here is essentially the approach that we're taking to solve, at least to some extent, some of these issues. So in order to understand the motivation of this work, first we have to talk about social dilemmas. And these are the subset of general sum games for which each agent acting rationally is going to lead to an outcome with less utility than that which would have occurred if they had cooperated. So the canonical example of a social dilemma is the iterated prisoner's dilemma. So first we have the prisoner's dilemma, which is this two-player general sum game where each player has one of two actions. They can either cooperate or defect. Both of them cooperate, they're better off than if both of them defect. But there is this dominating strategy of defecting where no matter what the other players do, you're better off defecting. Now, the interesting thing happens when you iterate this game infinitely many times, or when you have a stochastic number of interactions. And in this particular case, what happens is that the previous Nash equilibrium, which was this defect-defect equilibrium, becomes Pareto suboptimal, meaning that now there exist strategies, essentially cooperative strategies that are Nash, that have better outcome than this defect-defect. So one of such strategies is this tit-for-tat strategy. And tit-for-tat is a very simple strategy that consists of cooperating at the start and then subsequently copying whatever the other player did at previous turns. And it has a very interesting story as well. So tit-for-tat was discovered during this tournament, introduced by Robert Axelrod in 1980. And essentially, it was an IPE tournament where many submissions were made for possible strategies. This was on one history, prisoner's dilemma, iterated prisoner's dilemma. And tit-for-tat won with the highest average score. But more interestingly, in a second iteration of the tournament, and in this particular iteration, many strategies were submitted that were specifically designed to exploit tit-for-tat. Tit-for-tat won again with highest average score, which is quite surprising. So tit-for-tat is this kind of very robust strategy against a distribution of different strategies. And our goal, ideally, is to create reinforcement learning algorithms that are able to discover similar strategies on their own. So the question is why to study these social dilemmas like IPD. They seem very toyish, right? But the simple answer is that they show up everywhere. So interactions like merging lanes in the highway, things like the climate change problem and controlling climate emissions, to even like the policy that we currently have for nuclear arms proliferation. These are all instances of social dilemmas. So I think in a future where multi-agent systems interact in the real world, we should be thinking about this failure of reinforcement learning. So what do I mean by this? So it's actually quite discouraging what happens when you run reinforcement learning on the IPD, this very simple matrix form game. So in 1996, Sandholm and Kratz were able to show that two Q-learning agents playing IPD converge to mutual defection. In 2018, Forster was able to show that policy gradient methods have the same fate. Essentially, two PPO agents will also converge to this mutual defection strategy. In a more recent work, under some very strong conditions of optimistic initialization and one-step and self-play, Q-learnings are able to learn this more cooperative Pavlov strategy. So essentially, we have this very interesting dichotomy with reinforcement learning for different types of games. So on one hand, we're able to beat professional players in zero-sum games. We're also able to create agents that cooperate with humans in very difficult cooperative games like Dota. But now we fail in this very simple matrix to action form game. So definitely, I think we have a big problem here that we should be taking more seriously. And this is worrisome for many reasons, right? We're starting to see these agentic systems being actually deployed in the wild. So things like this Google agent-to-agent protocol, which manages resources across firms and within Google. You also have Walmart starting to use these autonomous negotiation platforms to negotiate with small vendors. And of course, the canonical example of these driverless car policies of Waymo and Cruise that are actually being fine-tuned with reinforcement learning. So always the effect on this greedy reinforcement learning is actually becoming a real threat. And you can think of these inter-firm interactions using these kind of protocols becoming competitive and leading to inefficiencies. Similarly, these greedy negotiating agents of behalf of Walmart may exploit small vendors in negotiation. And we want to also avoid this kind of aggressive driving that could arise from pure reinforcement learning fine-tuning. But these are just a few of the examples. So what is the solution, or what is a form of solution, is this opponent shaping paradigm. And this opponent shaping paradigm changes a little bit the standard stationary assumption of reinforcement learning. Essentially, instead of assuming stationarity of the environment, we're going to assume that the other agents are learning agents. And this is a particular flavor of opponent shaping. Ideally, what you want to do is influence the learning dynamics of other agents in such a way that it's beneficial to you. And you can do that in many ways, but in this particular case, we do so by assuming that the policy of other agents is differentiable with respect to the parameters of the first agent. And if you do this assumption, you plug this into the policy gradient theorem, you end up with these two terms, essentially just your regular advantage policy gradient that you get from PPO and any other reinforced style algorithm. But you also get this opponent shaping term, which is essentially trying to induce the opponent, in this case, player 2, to take actions that are beneficial for the agent. Now, there is this big limitations with previous opponent shaping algorithms. So they make very strong assumptions about the other agents. So things like accessing policy parameters, knowledge of the specific learning algorithm. They also have very complicated gradient expressions. So gradients that can either be approximated by the Taylor expansion or that require higher order terms like Hessians. And all of this leads to this kind of algorithms to be unable to scale beyond very simple social dilemmas, like the iterated prisoner's dilemma. So essentially, we want to be able to develop algorithms that scale. And that's what we do here. So I'm going to be introducing now advantage alignment, which is a proposed solution to this. Advantage alignment makes two assumptions about the other agents that it interacts with. So first is making the regular reinforcement learning assumption, which is that each agent is trying to maximize their value function. And the second one is going to do is essentially this opponent modeling assumption, which is just going to say that the policy that the other players play is going to be proportional to some exponent of the Q values. And the beauty here is that this Q value expression, the Q value is simply this expectation or this joint policy distribution. It depends on the policies of both players. Therefore, you can make the policy of player 2 differentiable with respect to the parameters of theta 1. But okay, you do some mathematical tricks, and what you derive is this kind of expression. So under these two assumptions, you can show that the opponent shaping term actually simplifies to this. And this is some function that depends on the advantages of the past agent, of the first agent, and the advantages of the second player. This is for the two-player case. So this is very powerful because now we can isolate the log probability terms and plug this expression into any reinforced style reinforcement learning algorithm. So what do I mean by that is now you can just substitute the advantage that you use in your policy gradient algorithm, your favorite flavor, whether that's reinforced, PPO, it doesn't really matter. But you substitute your advantages by this expression. Essentially, the first term just corresponds to your regular policy gradient, but the second term depends on the sum of past advantages of the first player multiplying the advantage of the second player at the current time step. And this has a very interesting interpretation. So if the sum of past advantages of the first player has been positive, essentially now you're having this kind of cooperative behavior where you're intrinsically trying to maximize the utility of the second player. It's kind of like cooperating with my friends. In red, you get this retaliatory behavior. And what I mean by that is that if the sum of past advantages for the first player is negative, then what you're actually trying to do is to harm the second player. So just from these assumptions, you can derive some very interesting gradient formula that you can interpret. So we also have some theoretical results. For those of you who are familiar with opponent shaping, we essentially unify opponent shaping techniques in the following way. We show that Lola, the most famous opponent shaping algorithm, is also implicitly doing this form of advantage alignment. Similarly, our previous work, Loca, is also doing advantage alignment, and by advantage alignment, I mean this kind of advantage multiplication between the different players. But more importantly, we're able to show that this kind of opponent shaping algorithms are also preserving Nash equilibria. So with advantage alignment, empirically, you can record it for that on the iterated prisoner's dilemma. And these are results on full history IPD, so not limited to single-step IPD. But more importantly, now that we have a very simple modification to PPO, we can scale to games with much more complicated dynamics. And that's what we do in Melting Pot. So in Melting Pot, you have this kind of environments that are high-dimensional pixel spaces. They're also partially observable because each one of these players can only see a tiny window around them. You also have temporally extended delayed rewards. So they're very, very complicated environments that also have multiple players. So I've talked about the two-player case, but advantage alignment is very easy to extend to multiple players by adding terms. And in this kind of environments, what we're able to show is that these advantage alignment algorithms are able to essentially cooperate with each other. So in this kind of environment where you have apples, you're trying to prevent agents from eating all of the apples and extinguishing the bushes. Advantage alignment agents are able to do so even when they interact with aggressive invaders. And essentially, this is what we show here in the numbers. We outperform most of the baselines that already exist, all of the baselines that currently exist. So that's all, and thank you for coming. I'll take any questions.
Any questions?
So you, excuse me, you can handle partially observed states, but what assumptions do you make about what you see about the other player? Do you have to see their actions and rewards? Because you have to estimate what their advantage is, right?
Exactly. So the assumption that we make is being able to observe the rewards. So if you are able to observe the rewards, you can learn these advantages on yourself. Ideally, we want to relax these assumptions, but this is something that you could do with communication, hopefully, in the future. Like assuming that the communication is trustworthy, maybe you can ask the other agents what they care about and relax it.
Any other questions?
So in a slide in between, you had this, different zero-sum coordination, and you said about your game, right? Like, how does your method, like, maybe help? Can you give some intuition about this? Yeah.
Yeah, I think the main intuition is this one, which is what the policy gradient term is doing, right? Like this multiplication of past advantages, right? And I think I gave a short description of what this is doing. But intuitively, what it's trying to do is, this is the mathematical expression, but this comes from the intuition of how we built this algorithm in the first place, which is trying to control the Q values of the opponent. So if you take an action that I don't like, I can very easily control the Q value for that action by punishing it. So you hit me, I can hit you back. Similarly, I can do incentives, right? If there is a a beneficial action for me, I can give you an incentive so that you take that action more frequently. So you tend to find this cooperative solution in the mixed, in the general sum case, essentially.
Okay. Let's thank the speaker again.